Hello kids, it's teacher Didi for a new online lesson. Last time we saw collision and energy transfer, what makes roller coasters go so fast. And yeah, we need to do that because I forget. I do lesson 2 before lesson 1. But it's okay. How is your body similar to a car? We will see that now. So we talk about energy these days, but I think it's related to electricity. It's not exactly the same, but there is a relation between energy and electricity. You can create energy with electricity, and with
Hi,
energy
it's
you can
Doug.
create
Have you
electricity.
ever thought
So I think it's okay for you, and it's interesting video. Okay, let's start.
about this? We use the word energy in some totally different situations. Like, on the one hand, we talk about energy and our body. Think about when you're running around. People might tell you, you seem hyper, you have lots of energy. Or think about when you're sick, for example. When you're really sick, it's the worst feeling. That feeling where you just don't even feel like moving. You just lie there, barely wanting to do anything. We say, ugh, I feel like I have no energy. So that's energy in our body on the one hand, but we also talk about energy when we think about things that aren't even alive, like computers and smartphones and cars. We all say these things need energy in order to work. Could it really be the same thing? After all, we get our energy from what? Food. But cars, they get their energy from gasoline. Or if they're electric cars, then from batteries. Could it really be that the stuff that's in food, whatever this thing is that we call energy, is really the same thing as the stuff in gasoline and batteries? What do you think?
Okay. Do you think the energy used by people and the energy used by cars is the same thing? Why or why not? Think about that. 5, 4, 3, 2, 1. Okay, let's have the answer.
We've all heard that we get energy from eating food. To make that a little more real, consider this guy. This is former Olympic swimmer Michael Phelps. He's won more gold medals than anyone in history. Athletes who compete in sporting events know that they need a lot of energy. Well, what do you think Michael here eats for breakfast? He eats 3 fried egg sandwiches with cheese, lettuce, tomato, fried onions, and mayonnaise. That's a pretty big meal. But that's not it. He also eats French toast and pancakes and grits. Oh, plus an omelet, all for breakfast. That's a ton of food. But all of that food has energy stored inside, which Michael Phelps's body uses in order to move his body and swim as fast as he does. Still, is this energy that's stored in our food the same energy stored in gasoline, the energy used to power cars? I mean, people can't run on gasoline. But think about what happens when a car runs out of gasoline. Sometimes people have to get out of the car and push it to make it move. That would be a car running on people. And since people run on food, technically then, this is a car powered by the energy stored in food. Still, that seems a stretch. Could a car be powered directly by food? It is possible. A car can't digest food the way our stomach does. But believe it or not, this truck has a special engine that runs on French fries. The drivers collect the oil that the French fries cooked in and pour it into the gas tank. The truck's exhaust even smells like French fries. Now, here's a bus that runs on beans, soybeans specifically. They grind up the beans until a liquid oil comes out, and that gets turned into fuel. Someone has even created a race car that runs on chocolate. So, just like people use the stored energy in food to move, cars can use the energy in food to move too. And it's not just cars either. For example, some toy rockets are actually powered by Sugar. You've probably heard that sugar is one of the foods that has a lot of energy stored in it. Now, keep in mind, that doesn't mean it's healthy for you. But check this out. This is a video of someone using sugar as energy for a rocket. First, he melts the sugar in a pot until it's golden brown. Then, he pours the melted sugar into the rocket, just like this. When he lights the fuse, the rocket blasts off into the sky. Wow, that gives you a real sense of just how much energy is stored in sugar. All of this is just to show you, energy isn't just some cute expression that we use, it's a real thing. Energy may not be something you can see or hold, it's not an object, but it is real. Inside a battery, inside of food, inside of gasoline, there is something stored up, which when it gets released, makes things start moving. That thing or ability to make something start moving, that's what energy is. Batteries, food, and gasoline are just a few of the things that contain energy stored inside of them. But there are even other things that can store energy. We've talked about real cars, but consider something like this, a wind-up toy car. Where does a wind-up toy car get its energy from?
Okay, I will activate my webcam. So, where does this get its energy from? You see the spinner? Move the spinner, and there is. Well, you will explain better than me.
Wind-up toys are a classic toy of childhood. I'm sure you've played with one before. You know you have to wind it up to make it move, but have you ever thought about what's going on inside a wind-up toy? Well, have a look at this one. As you open up this wind-up toy, you immediately see there's no battery inside of there. So where does it get its energy from? How does it move? This thing right here. This piece of metal here that's all coiled up is a type of spring. When you twist the knob, you're winding the spring tighter and tighter. You see that? A spring is something that can store energy, just like a battery or just like gasoline. The coiled spring inside of a wind-up toy car might not be something you've seen before. The more classic-looking spring, like this one, is one you might be more used to seeing. But it's the same kind of spring, like if you've ever used a pogo stick. As you press down on the spring, it stores energy, then releases it again, causing you to bounce back up. Where else can you find energy being stored and released? That's something we'll keep coming back to throughout this unit. You're going to get to explore and play around with energy. You'll even get to use what you learn about energy to design fun and useful things. Starting today. Let's consider one other way that energy can be stored. In these rubber bands. If energy is the ability to make something start moving, then rubber bands are definitely something that can store energy. One of my favorite things to do, and with this you have to be careful, is to use a slingshot. It's basically a huge rubber band that you pull back and then try to launch something. Like in this case, launching apples at targets. You can see when you pull way back on the rubber band, the apple can fly all the way across the field. Now, I hope it goes without saying, but never use a slingshot indoors. Now, you can even use rubber bands to make rubber band-powered racing cars, where the more you wind them up, the farther and faster they go. There are so many creative ways of using rubber bands to make something move, like even this toy airplane. Now, why is it that the more you stretch a rubber band, the faster you seem to make an object go? Why do you think that is?
So, if you stretch more rubber band, you will give more energy. It's like what we saw at last lesson, potential energy.
In today's activity, you're going to build a new amusement park ride for the company Acme Amusements. The ride is called the Twist-O-Matic, and it works by twisting rubber bands, which store energy. When the rubber bands are released, they use all that stored energy to spin the riders around and around and around. Now, the real full-sized amusement park ride hasn't been built yet, so today you'll be testing a model, a smaller version of the Twist-O-Matic. Your goal is to figure out how to make the most exciting ride. We'll show you how to get started, step by step.
Okay, kids, so we cannot do the activity.
Find a partner.
But maybe we'll see the result.
You'll be The Twist-O-Matic might not seem like any kind of ride in real life, especially not one made from rubber bands, but there are actually amusement park rides that make use of elastic bands, like this, called the Slingshot ride. And even though there's no spinning involved, what's happening in terms of energy is very similar. When you either pull back on a rubber band or when you twist a rubber band, like you did in the activity, the energy from your body gets stored in the rubber band. Or to be more exact, the energy from your arm muscles is getting stored in the rubber band. That's energy that came from the food you ate. When the rubber band is released, the stored energy gets released too, which is why your Twist-O-Matic would spin. But why did the thick rubber band spin faster than the thin rubber band, even though you gave them the same number of turns? We're hoping you noticed that the thick rubber band was a little harder to turn. Because you had to use more energy to turn it, that means more energy got stored in that rubber band. Which is also why when you released the rides, the thick rubber band spun around a lot faster compared to the thin rubber band. In other words, the more energy you put in, the more energy you get out. The more energy stored in something, the more energy it can release. If you did want the thin rubber band to go as fast as the thick one, then you had to store more energy in the thin one by turning it around more times. Again, because you added more energy, it released more energy. It spun around faster. Notice how there's a connection between energy and speed. The more energy you store in something, the faster it goes when that energy is released. Or to put it another way, if you want something to go really fast, you're going to need a lot of energy. And that makes sense with other things you've probably noticed before. For example, the faster a car goes, the more gasoline it uses. The faster an Olympic athlete wants to move, the more food they need to eat. What if we had used an even thicker rubber band in the Twist-O-Matic? Not one this thick, but one more like this. Well, let's have a look. Let's spin it up. It takes a lot of effort to spin this one. Whoa, you see this? Look at how much that thick one spins. If you liked using rubber bands as a way of exploring the connection between energy and speed, definitely check out some of the other activities you can try, which we've linked in the optional extras. Have fun and stay curious.
Okay, kids, so we'll see if we'll try to watch if there is other video. Okay. And after that will be the end of the lesson.
What are the ingredients we need for this experiment? Things, food and fire. Amy Kress from the Imagination Station joins us now. And Amy, this experiment, of course done safely, is going to show us how calories burn with a little exercise.
Not quite.
Okay.
We're gonna be burning some calories today, but not the traditional way, not the exercise.
All right, so you're not going to put me to work right here.
No.
We're going to use fire.
Right, we're actually gonna literally burn calories.
Sweet.
That sounds good.
All right, sounds good. What are the ingredients we need for this experiment? I'm
Okay.
guessing we need fire.
We need fire.
Okay.
For combustion, we need fire, we need fuel, and we need some oxygen.
Okay.
So we've got all those things today. Our food over here, we've got some marshmallows and cheese puffs. Those are going to be our fuel. Help get the combustion going. We've got our fire right here in this heavy duty torch right here, and we've got some liquid oxygen. That's going to help us out a little bit, kind of boost it up.
All right, first step here, what do you need me to do?
All right, well, I want you, which one do you think has more calories in it, the marshmallows or the cheese puffs?
Cheese puffs?
All right, that's a good guess.
You're not going to make me eat a whole bag, are you?
I'm not.
Okay.
What we're going to do, like I said, is we're going to light them on fire.
Okay.
You know, calories are just a measure of energy. So why don't you go ahead and scoop a handful of marshmallows into this bowl right here.
Okay.
We'll try the marshmallows first.
Okay.
Okay, so we're going to, when we light them on fire, get a little more than that.
Get a little more than that? I like that.
When we light them on fire, we're going to measure the amount of energy given off, and that's going to tell us how many calories are in it. So the bigger and the brighter the flame, the more energy and the more calories.
Makes sense to me.
Okay?
Okay.
So what I'm going to have you do, I'm going to get this blowtorch ready for you.
Okay.
Okay, ready?
So that.
There we go.
Right.
Can you handle it?
I hope so.
Okay, there we go. So I'm going to pour this liquid oxygen on here. Okay? So here's our liquid oxygen. On the count of 3, I'll pour it, and you just flame it, and we will see what happens. Go ahead. 1, 2, keep it going.
Yeah.
All right, good. Take a step back. Okay, I'll take that flame torch for you.
I can only play with toys like that for so long.
Right.
Okay.
So that's a pretty good sized flame, right?
I like it.
Pretty good, pretty good. And our marshmallows, woo!
Yeah.
We've got a good reaction going on.
That's science for you. You just can't make this stuff up right here. Very cool.
And I like the smell of it too. It kind of smells like a
summer
bonfire. Summer, yeah. Smells very good.
Who wants to roast marshmallows now?
Right.
A lot of people like them crispy like that too.
I do.
I've never been a big fan of that.
I like it.
I like it just lightly toasted.
All right, so that was
pass
cool.
on that.
Let's go ahead and try the cheese puffs now.
Okay. We had it seemed like to me a pretty good flame going with that. And again, the amount of flame distinguishes how much energy is being released, correct?
Right, yep. So however much energy is stored up in there, it's going to be released when we light it on fire.
Okay.
Okay. So let's try this. I'll do the flame.
We've got to make sure these are real cheese balls too. They
They might be a little stale.
No, they're
Are they
pretty
okay?
good.
Okay.
Cheese balls never go bad.
All right, good. All right, so let's try this second one. Here we go. 3, 2, 1. Whoa, big flame, right? Isn't that amazing? A big pillar of flame there.
I'm at the hibachi grill right now.
I know.
That is
very
cool.
bright.
And look at this. If we could get in here as the fire's going away, we basically extinguished our material that we were burning.
We did. We actually have a little extra oxygen in there if you want to throw a few more cheese puffs.
All right.
All right, so our cheese puffs had a much bigger flame, right?
Yes.
So we've got the bigger flame, more calories in that, and that's one way we can tell how many calories are in our.
Okay, kids, it was last one video, so you can see we can store energy in food too.
Ready? Yeah. Paddle.
Oh, we already see that.
Back. Yeah. I'm in the foot.
Okay, kids, so put off my webcam. I'll take my. Okay, kids, so it's the end of the lesson for today. Have a great day. Take care of yourself. Bye bye. See you soon.